We're gonna learn about latent heat right now.
Is this gonna be on the energy test?
Yeah. Last day, we learned about Q equals mc delta T, yeah? That's thermal heat. So as you put energy into a substance, it gains temperature. But not the same amount for different substances, yes? Let's say that we start with a block of ice. Mark, ice is solid what? Good. Here's the interesting thing. The specific heat capacity of water, does anybody remember the number?
4,184.
Good, 4,184 or so. That's joules per kilogram degree Celsius or degree Kelvin. So to increase the temperature of a kilogram of water, you got to put in 4,184 joules. That number is actually Can you pause it? That number is actually different for solid water than it is for liquid water than it is for gaseous water. They're actually different numbers. So if you start with ice, let's say this is temperature, okay? If you start with a block of ice, when I was your age, I used to, I had a lot of interactions with ice. This was very cold where I lived. And the lake would freeze. And you could drive on the lake. That's where I learned how to drive. You'd hit the gas and you would just go on the ice. And Hayden, if you put energy into the ice starts to rise in temperature. Can ice be colder than 0 degrees? Yeah, it can be way colder. So let's start it at, Chris, what temperature you want to start at?
0.
No, we got to be colder than that.
-3.
No, way colder.
-6. No, I can't change.
When I was your age, the buses would stop running at -36. And we would watch the thermometer. Get colder. And then it'd be like -38. Yay! Let's start at -38 degrees Celsius. It's ice, right? This x-axis is energy. So this is the energy we're going to put in. In our thermal formulas, it's Q. But you understand it's energy. So we put energy into the ice, we shine a light on it, or put a heater on it, or whatever. And the temperature of the ice goes steadily up. Like this. Okay, it's a little less than liquid water. I think it's about 2,000 to C for ice. We can look it up later. But it goes linearly up until it gets to what temperature? 0. Now here's the interesting thing. If you guys are doing something else, can you go somewhere else? It's okay, you can. You never leave. Not in 20 years have I ever, except for, did I tell you about?
Yes, you did.
I'm repeating my stories now. It's time for a long weekend. When you get to 0, what happens to ice at 0? Huh. But not right away, actually. You put more energy into the ice and it stays 0 degrees Celsius. So you have a time where it's just 0 and it just stays 0. And you can heat it up more and it doesn't melt. Then at some point you've put in enough energy and it turns into water and it goes like this. And it starts rising in temperature again. This part right here is called latent heat. And you can say it's equal to the mass of the substance times the latent heat. Now there's a heat of fusion and there's a heat of vaporization. And they're both called H. You can say HF. And that is the energy needed to melt or freeze. It's the same in reverse. Okay? So that's this H, and this would be heat of fusion. Okay, then we go up, and the water just keeps going, MC delta T. It's no problem. You just put every time you put in 4,184 joules, it rises 1 degree, and it keeps going up until what temperature? Until 100. What happens at 100?
Boil.
It's going to boil. Right away, do you think?
No.
No. Actually, when you get to 100, it has another one of these. And this is a different heat of fusion again. I can't remember which one is bigger. We'll look it up. This is a different cube. And this is called the heat of vaporization. And that's the energy needed to evaporate. What's evaporation in reverse? Very good. Or to condensate. So if you're going to boil something, you have to put energy in. If you get water vapor condensing as a liquid, that actually gives you energy. But it's the same amount in reverse. And then after you have water vapor, and it continues up like this, and it goes on forever, you can make water vapor as hot as you want. Okay, so you can see, and I'll show you, it's actually, the list is in here. I'll look it up for you, and I'll put it on the board. Maybe, if I can find it. 253. If you're looking in the red book in 253, it'll give you a list. I'll put it on the board right now, just in case you are curious. So that's really all there is to know about latent heat. And here's the values. I'll give you the values. You don't have to memorize them or anything like that. So you'll see water ice is 33,400. Wow, that's a lot. And the vaporization is 2.26 times 10 to the 6. So you have to put in this amount of energy. If you're going from ice, like in our graph, the ice to water takes this amount. That's not like per degree. It's the energy you have to put into to melt the ice. It's just one time. So you put in this amount, and then you're from ice into liquid. And then you put in this amount. This is 2.3 million joules you have to put in to go from liquid to vapor. So I'm going to ask you this. Or I could ask you, hint, hint, nudge, nudge, wink, wink, on a test. I could say if you had water at -6 degrees Celsius, how much energy would it take to get the water up to 125 degrees Celsius? You have to do 5 things. you have to say, use the C for ice, get it up to 0, MC delta T. Then you have to take the fusion energy, add that, just once. Then you use the C for liquid water, MC delta T. Add that on. Then you take the heat of vaporization, that's the energy you need to boil it. Add that in just once. And then you have the MC delta T for water vapor. So you do MC delta T, and then the MH, and then MC delta T, and then the MH, and then MC delta T. So you have to add in the phase changes. You understand? Yeah, let's do an example. Let's stop the video first. That's all the notes that you have to know.